The ball becomes heavier and stronger.
Exactly. So why does it become strong? Because you are compressing the ball from all of its outside direction inwards. You are squashing it down. That's what gives it the strength. In another way, I can put this is that, let's say, if you have a bunch of wire which are individual to each other, it will give you, it might not give you much strength, but if you wrap it around with a very tight string, it's gonna become a pretty strong thing, right?
Yes, sir.
That's exactly what is happening in Prince Rupert's drop. When the cooling process got started, the outside layers became solidified, but the inside did not solidify yet. When the Prince Rupert drop was hot Prince Rupert drop was dropped into the water, the outside part was cooling down pretty fast, but the inside part was not cooling as fast, and as a result, it was squashing onto the inside very strongly, which made those large part of the drop extremely strong because it was squashed from the outside surface inward very strongly. But this whole thing was continued in a chain formation, as the person showed, the distance showed over here, all the way up to the thin part of the chain. So that's why whenever that, so it was pretty much impossible to break that or shatter that piece from the face. For example, here is another video which we might as well see at the end of the class. If you are interested, I'll see it with you. I'll show it to you. Just remind me of this. You'll see that even shooting AK-47 bullets to the face, the bullet simply shatters away as if the bullet is nothing. The glass stays still, which is unbelievable and amazing at the same time, but it's true.
But sir, how does
armor বানায় তাহলে তো ওটা indestructible এর মতো হয়ে যায়।
and how can they not make other glasses like this?
Because you have to have exclusively this round shape, and I mean, you cannot essentially make a marble like this because you have to pour really hot glass into cold water. There is a certain point of temperature that you have to raise up the glass to achieve these structural properties. And I mean, it is pretty difficult to make physically a useful shapes. For example, a glass, I mean, the drinkable glass or jug or mug, which has a specific shape, which will also maintain that behavior. That's pretty difficult to do. But you can make that kind of droplets only if you allow it to cool on its own. So molding a wanted shape with that physical property in it is actually quite difficult. So far I know, impossible, but you can allow it to form in its natural shape that can give you this property. Yeah, that's just amazing. This is the first video that I came across of Destin, somehow smarter every day, and I feel in love with him. I'm still in love with him. Non-platonic love, that is. Non-platonic, platonic love.
I mean, it's more how to over the play.
I mean, asexual love. I mean, I just love him as a science person. So moving on to our regular part, which is the lectures. So I'm gonna go ahead and, oh my God. What? Did I not add this? এই পিচ্ছি কি তোমাদের গ্রুপে আছে?
এটা কি
আমার নয় স্যার।
কোন স্কুল?
I don't know. New kid. Was she supposed to be in our
ক্লাস
নতুন জয়েন করেছে? Not add me to the group.
What the hell? I did not.
Class 9 নাকি class 8 স্যার? Sorry, class 9 নাকি class 10?
Damn it, I forgot to add this kid. And I just had a very amazing class of class 9. Why am
more
I,
amazing than our.
why am I like this?
ক্লাস 10 এর স্টুডেন্ট গুলো কিরকম?
They're amazing so far.
So we love you like this.
তো বলে পাঠাইছি আপনার কাছে, থ্যাঙ্কস দিন।
আরে কপাল।
Please don't cry, sir.
আচ্ছা ঠিক আছে, never mind. তোমাদেরকে কতটুকু পর্যন্ত পড়াইছিলাম?
Reflection.
Okay, so today we're gonna start copifying the refraction part. So we did cover the whole part about the reflection and the plane mirror and everything. And today we're gonna start talking about the refraction thingy. My bad. আচ্ছা, রিফ্লেকশনের বেসিক কয়েকটা আইডিয়া বলি তোমাদেরকে, যেসব তোমাদের বুঝতে সুবিধা হবে। এন্ড তোমরা অনেকে রিফ্লেকশন পড়ছো, লাইট চ্যাপ্টার তোমরা অনেকে স্কুল থেকে পড়ছো, যারা পড়ো নাই তাতেও সমস্যা নেই। I'm gonna explain every part every once in a while. The first thing that I always start the reflection lecture with this equation. Do you guys know this equation? What does this equation mean?
Velocity equals to frequency into lambda.
Lambda means wavelength. Beautiful. So this is true. This is a true equation for any wave that passes through that goes around, whether it's a mechanical wave or an electromagnetic wave, doesn't matter. For typical cases, for light waves, we tend to change the symbol for velocity a little bit. For light cases, we tend to write the formula in this shape because the speed of light is usually represented by c, which is basically the speed of light in air or vacuum. So c is the specific symbol for speed of light, which is approximately 3 to 10 to the power 8 meters per second. So sometimes that can also show up in your working. Nothing to worry about. In this case, c means the speed of light in vacuum. Exclusively for this scenario, we can write it like that. For other medium, for speed of light in other medium, we might use a small subscript. For example, if I want to write, let's say, the speed of light in water, I can write it like this, CW. Speed of light in glass, I can write it like this, G. Speed of light in something else, what, oil, let's say, I can write it like this. So something like that. We can use certain subscripts to use different values. Now, one point you should remember as well, that once you produce a certain light wave or a certain wave from a source, the frequency is a constant property which does not change, which means if you have a light wave that travels through air and then it enters into a water medium, this equation is going to change in this format. CW equals to F into lambda W. See if you can understand this part first. Because the F would remain F. F will not undergo any change. What will change are these two variables. Speed of the wave, that will affect the wavelength of the wave. See if it makes sense.
What was C again?
C is the speed of light. Only for the light, we use the symbol C, which is a replacement for V. So this is going to happen. If you write the same equation for the glass, speed of light in glass can be written as frequency into lambda glass. You can similarly write frequency into lambda of oil, so on and so forth. Point that I'm trying to make, that the frequency will remain same and the speed and the lambda will change proportionately. Proportionately means that they would have the same percentage change for both of them equal. So this is the important bit that I want you to understand. Then the second thing that I need you to remember, which helps to figure out a lot of figure, is that try to remember this figure as best as you can. Let's say we have a medium boundary over here. Let's say this is the medium boundary. Slightly thinner line is recommended. Why is it so difficult to draw perfectly horizontal lines?
Sir, how are you?
Should I try to use my right pad today? Do you kids
Try
mind
for it.
if I try my right pad with you kids today?
Yes, no sir.
Right pick,
No,
sir.
sir.
Yeah, you
No
can
problem.
use.
Ekটু wait করো. I have my right pad waiting up, and I mean waves chapter might as well be the optimum chapter to utilize the right pad. Don't you think? There's a lot of drawings are here. Right pad is the electronic writing thing, which you connect with your USB cable or via Bluetooth or something, whatever the connection mechanism. But I have a USB thing, and I can connect it with the. I have the,
Bamboo stylus nahi sir.
yeah, I have the one by Wacom. That's something that I brought
Oh, chintzy.
quite a bit earlier, but I haven't been using it because I got used to, or not used to, I got comfortable with the Microsoft Paint. I mean, I know that I could get more comfortable with this product, but I'm not sure how this is gonna work. So let's say if I try this, which is the better software, or software, I have what are these things? Okay, I did some.
Sir, are you using the mouse and the right pad at the same time?
Apparently I am, but you can actually use to create more whiteboards. Create multiple whiteboards. Oh,
This looks like a person wearing a top hat. Yep.
so cool. Okay, so if I try to write, let's say,
স্যার সাউন্ড কমে গেছে আপনার।
Sir, কিভাবে শোনে?
sorry. I just dropped off my microphone. This should be better now, or regular.
Not better.
Okay, I don't want yellow, so I want black and okay. This is nice. I can move my mouse and then I can write. So let's say I'm gonna write over here. Wow!
Is something wrong, sir?
No, this is amazing. I can see my handwriting.
So change হয় না তো?
আচ্ছা
You see,
একটু ইমপ্রুভ হয়েছে।
this is my actual handwriting. God damn it!
Sir, I remember it used to be more beautiful.
না কম্পিউটারে তো একই icon ছিল।
Agreed, yes, sir.
This is amazing. Yes, I want this. Okay, so I have this. Okay, so I have these equations, and then let's say I'm gonna try to help you to remember one of the simple figure that we actually go by. Let's say I'm gonna try to show you some light rays. So let's say I have a horizontal line. How can I make sure it's a horizontal line? I mean, is there an auto detector for the horizontal line? Or maybe not. Doesn't matter. So let's say this is a boundary medium. Let's say here we have air. So let's say this is our air medium. And let's say here we have water or glass, anything else. Let's say I'm going to write glass. So this is the medium. So let's assume that these two medium are infinitely big. So I'm not essentially computing the two mediums anywhere on the other side. So I'm keeping the medium. I'm only showing you the boundary. Let's say one light ray. Let's say I'm going to label this light ray, incoming light ray by what? By blue. Okay, blue works. So let's say I'm going to show it by blue. So let's say one light ray that comes and falls. Wow.
Sir,
বলো
এর মধ্যে pressure sensitivity আছে না?
কি
মানে আপনার পেন্টে প্রেসার সেনসিটিভ যদি ইউজ করতেছেন
কি সেনসিটিভ
প্রেসার মানে চাপ দিলে মোটা লেখা আস্তে দিলে চিকন
Nah, I don't think so, yes, sir.
I don't think so. সোল সারটা মনে এরকম using pressing a certain button, I can make it a dotted line, which can look like this. I think I can select a certain part using this one. Oh, okay. I don't know what just happened.
Sir, did you
I'm
do
having
this by pressure? As Yahoo said.
Okay, never mind. This is just,
Sir, why is he laughing at this?
I might as well prefer to. How can I delete this? আচ্ছা, দুইটাকে একসাথে ইউজ করতে পারলে অনেক উপকার আছে। Wow. This looks
So
like a
this is
poop.
also like paint shading.
This looks like a
Sperm-এর মতো
poop. Blue poop. Maybe out of the Monster Incorporated বড় মনস্টারটার নাম যেন কি ছিল? Not the green one. Mike Wazowski now. Green one was Mike Wazowski.
So
The blue one was Sullivan. Sullivan.
Sullivan, exactly, Sullivan. Yeah, that blue thing might as well be his poop. I'm not sure. So yeah, so let's say we have the air and the glass boundary over here. A certain light ray is coming in from here. So let's say, okay, I have to learn how to use these buttons on this pen. So let's say this is the incident ray, and just to make sure that we are, and let's say from this point we're gonna have the refracted ray, which is gonna bend a little towards the normal. So let's say this is my refracted ray. Now I'm gonna show you multiple things on this figure. So keep your head tight. So let's say I'm gonna show you the normal with the red line. So let's say this is my vertical normal. I'm pretty sure there are better softwares to write upon where they detect your horizontal and vertical lines automatically. So sir showed me some of these magical tricks.
স্যার এখানে একটা স্কেল আছে, আপনি কি একটু ট্রাই করবেন নিচের দিকে?
করেন।
আপনার হাতে গ্লাভ পরছেন?
না আমি ফ্রি হ্যান্ডে রাখতেছি।
আচ্ছা, ফ্রি হ্যান্ড ঠিক আছে, একটা গ্লাভ পরছেন।
স্যার ওয়ান নোট আরো ভালো।
Yeah, that's what I've been told as well, but I'm trying to figure out every single software because this I'm trying this for the first time. Okay, kids, bear with me.
Okay, sir.
So far it's not very fast, but I think I can gain my speed on this one. Okay, the reason I had to choose this once again is because I want to do this.
স্যার আমার কিছু প্রবলেম ছিল এর আগের লেকচার নিয়ে, আজকের ক্লাসের পর কি জিজ্ঞেস করতে পারি?
Okay, after the recording finishes you can.
Okay,
sure. So we have this incident and the reflected ray over here. Now a couple of things. Aste kotha nai internal kotha bolo na please. If you have questions ask me. So we have this scenario. What I want you to remember is that whenever light rays will travel from air to glass, it is going to bend closer to the normal. Now what do I mean by saying that closer to the normal? This is what we mean. If this air medium was continued further, if this glass medium did not even exist over here, then this light ray would not undergo this bend direction. This light ray is supposed to go in a very straight line along this part. So how can I draw a dotted line here? Kids, do you know how to draw a dotted line here?
There's probably an option here. That's curve thing.
Never mind. I'll just draw the dotted line.
স্যার আপনি কি একটু এক্সপ্লেইন করবেন যে কেন লাইট রে গুলো বেন্ড করে when the speed changes?
No. Let me tell you why no. This is a very good question. That the reason that why does that happen, that is usually explained by Huygens law of geometric construction and everything, which is not covered in your CA syllabus, not even up to your A2 level as well. So you are told what is happening, not essentially told, not covered in your syllabus that why that happens.
Okay, sir. Just that when the light enters the denser medium, it bends towards the normal, and the less dense medium, it bends away from normal, right?
Yeah, you have this much information of what happens, not why that happens. That is not entertained in your syllabus.
Okay, sir.
Acha. So this is what I mean, that if the a glass medium did not exist, this light ray that was coming through from the air, this was supposed to go in a single straight line like this. And that was supposed to be its original path. Because of the existence of this glass medium, there was a significant bend or change of direction of the light ray. Now this light ray bent from this alignment to this alignment. This is this alignment to this alignment. So this is essentially what I mean by saying that this is working. The light ray is bending towards the normal, because you can see that now the light ray underwent a bending from here towards this direction. I'm gonna rub off this arrow in a bit. I'm just showing you to give you this idea that what do we mean by the word towards the normal. This is what we mean by towards the normal. Does it make sense?
Yes, sir.
ঠিক আছে? So I'm not gonna use this angle, so I'm gonna rub off this angle কারণ এটা আমার লাগবে না। Vice versa আরেকটা জিনিসও হতে পারে। Vice versa আরেকটা জিনিস যেটা হতে পারে সেটা হচ্ছে that if we set up this light source, this point light source which was sending out this single beam of light, let's say maybe this might as well be a laser light source which sends out a single beam of light, and this is how the reflection is happening. Other than placing the light source in the air, we might as well place the light source inside the glass medium. For example, let's say somehow we put it inside the glass medium, and let's say we are aiming this light along this exact line. In that case also, if I just try to give double arrows over here just to represent this as a different light ray compared to the single arrow, if light ray was sent through this angle, then the light ray would also once again bend away from the normal. So it's gonna reflect out through this path, following this exact path. Now, what do I mean by this? What is important for you to understand that this light ray, if it was shot from inside the glass, would have gone along this path, which I am not trying to draw, but I will just try to visualize an extension of this light ray. So this light ray was going in this path, and if the air medium did not show up over here, this would maintain its journey in this path. Because the air medium did show up in this location, this light ray had to bend away from its original direction, away from the normal. So it made a bigger angle with the normal. That's the important bit. So important for you to understand that these pathways that we are drawing are not exclusive for air to glass or glass to air. These light rays could work in both of the directions simultaneously. Can we appreciate this information?
Yes, sir.
Yes.
These two light rays are not exclusive only for air to glass or only for glass to air. These two light rays can work vice versa for either direction. Light might be entering from air to glass, light might be going from glass to air, but in either cases they will follow this exact pathway, provided we place the light rays in appropriate positions. Or in other terms, what I'm trying to mean is that whenever light rays will travel from air to glass, they're going to bend towards the normal. When the light rays are going to travel from glass into air, they're going to bend away from the normal. That's the point that I'm trying to make. মুনাম বলো কোন পাটা বুঝে না, বুঝা গেছে এখন?
জি স্যার বুঝা গেছে।
আচ্ছা ঠিক আছে, beautiful. So that's the first thing that I want to make in your head. আচ্ছা এখন জিনিসটা হচ্ছে তোমাদের সিলেবাসে রিফ্র্যাক্টিভ ইনডেক্স একটা ফর্মুলা দেওয়া আছে। রিফ্র্যাক্টিভ ইনডেক্স is represented by the symbol n. N is given by sin I by sin r. This is the very default equation for our refractive index, sin I by sin r, which works pretty well because this is how we define the refractive index. However, I do not usually teach the kids in this fashion because this leads to a lot of confusion when you are doing the maths or the MCQs. So I'm going to show you a different version of this figure, but I'm not going to rub off this figure. I'm rather going to copy paste this one, and I'm going to pull it down over here and use and edit this figure for my purpose. So I have to now figure out how to copy this. I think
Control C by pulling the entire stuff up from a corner.
Okay.
That's the normal way we do it.
আচ্ছা স্যার ডাবল অ্যারো গুলো কি রিপ্রেজেন্ট করে এটা বুঝিনি।
ডাবল অ্যারো গুলো রিপ্রেজেন্ট করতেছে হচ্ছে the beam going from bottom to up, from glass to into air.
ওকে স্যার।
Why is it getting pasted here? How can I decide where to paste this?
Sir, I think the most perfect person to home solve with this thing is just sir.
দাঁড়া বলতেছি আমি। এই সবগুলো অপারেশনই করা যায়, কিন্তু কেমনে করে আমি পাই না, এখন শিখি নাই।
একটা ভিডিও দেখে নেন তাহলেই হয়ে যাবে।
ইউটিউব চেক করেন।
আহা,
স্যার কন্ট্রোল সি চাপ দেন, দেখেন হয় নাকি স্যার।
ওই একটা লাইন বাদ পড়ে গেছে, এটা হইলো?
কি লাইন বাদ করে গেছে স্যার? সব তো আছে। ওকে,
আচ্ছা, বুঝতে পারছি। Okay, let's say in this case, coming back to the same figure, I'm not going to label these two angles I and R as I and R. Let's say I want to replace these two angles using two other values. Let's say I'm going to, oh, it asked me to flip the pen over to erase this. Koi erase to hoy na.
স্যার আপনার কি ড্রাইভারস ইনস্টল করা আছে?
I think so.
ড্রাইভার ইনস্টল না করলে এই ফিচারসগুলো আসে না।
এত বড় কেন এটা? এটার সাইজ নাই? হ্যাঁ, ড্রাইভার ইনস্টল করছি আমি, ওয়াকম ওয়ানে ড্রাইভার ইনস্টল করছি। কি সমস্যা?
Sir, you should use the lasso select.
হ্যাঁ, ইরেজ করে কেমনে? এই ডটের সাথে আবার এটা সিলেক্ট হয়ে যাচ্ছে।
নাইস।
Sir, undo option আছে।
আচ্ছা, হইছে, কাজ হইছে। It's not as efficient as it's supposed to be, but it's gonna do my purpose. Okay, so in this case, let's say other than using the terms x, I and R, I'm gonna label these angles as x and y. Now bear with me over here, because this is the part that where I really need you to pay attention. The reason I'm showing you this angle x and y is to tell you one more information. So I'm gonna write a sentence over here. So let's take this out. The refractive index of the medium we are trying to represent / calculate angle / speed of that medium goes to the denominator side. This is the important bit that I need you to remember. এটা কিভাবে হয় মানে কেন এটা হয় সেটা আমি তোমাদের বলবো না, বাট এটা যে অ্যাকচুয়ালি লজিক্যালি কনসিস্টেন্ট সেটা আমি তোমাদের প্রুফ করে দেখাবো। সো বোঝার চেষ্টা করো। Have to understand. In this case, air was the lighter medium or faster medium, and glass was the denser medium or slower medium, which means the speed of light over here is larger, speed of light over here is slower. So I might as well label those speeds over here. Let's say this is, let me try label with blue. Let's say this is my C in air, and this is my C in glass, and with these two angles. Now, what I'm trying to show you that from this given figure, irrespective of the direction of the light, if you are trying to write out, let's say, if you're trying to find out the refractive index of glass, in that case, you have to write the equation like this. This is going to look like sin x by sin y. What is the logic? You're trying to find out the refractive index of glass. So the angle that was inside the glass medium should be at the bottom side. Or if you want to, you can also write the equation of the refractive index in terms of speed of light. For example, you can write speed in air divided by speed in glass. That is also possible. This ratio and these two ratios are going to be exactly same. Not telling you why, telling you what. So don't ask me why this is going to be equal, because not covered in your syllabus. So, but what you can also remember that the medium that for which you are trying to measure the refractive index for, that medium's angle or that medium speed should always show up in the denominator side. This is the important bit. Denominator side. Okay. So what do I mean by this? I mean, or how do I proceed with this equation? I mean, you might wonder, we knew with this from earlier, then what's the point of this whole x and y angle? Here's a bit. From this exact figure, you can also try to find out the refractive index of air with respect to the glass. That would look like this. This would be sin y by sin x, or that can also be given as speed of light in glass divided by speed of glass in air. The logic remains the same. The medium for which we are trying to measure the refractive index for, that medium's angle will go at the denominator side, or that medium's speed will also go in the denominator side. Now, I told you a bit earlier that I'm not going to tell you the proof of this expression, but I'm going to prove that it is logically consistent. Let me show you the consistency of this equation. Try to understand. The medium that is more dense should have a refractive index of more than 1. And the medium that is less dense should have a refractive index of less than 1. Because more denser medium means their refractive index is more, and less denser medium means their refractive index is less. Now, try to understand. If you have a look over here, between air and glass, which one is more dense optically?
Glass.
Optically, glass is more dense. Now you might wonder, what's the whole point of mentioning the word optically? What does that even mean? That has something to do that physical density and optical density, they are not same for materials. Physical density means mass by volume. That would not essentially dictate its optical density, which is how much a light is going to bend as it changes its medium. For example, if you consider between water and kerosene is an oil. Physical density wise, oil floats on water. So kerosene is less dense than water in terms of physical density, which is mass by volume. But in terms of optical density, kerosene happens to be more optically dense compared to water, which means light will travel faster in water and slower in kerosene. So physical density and optical density are two different things. Optical density is measured in terms of how fast the light travels to that medium, whereas physical density is measured in terms of mass per volume. So they are not the similar quantity. They are not anyhow related. They are not even distant cousins. They are different species altogether. That's what I'm trying to put here. বুঝতে পারছি?
Yes,
So
sir.
don't confuse these two terms at any point. It's important that you know this thing. Okay. So what I'm trying to show you over here is that because glass within the comparison of air into glass, the glass is a more a more dense medium. So essentially the refractive index of glass is supposed to be higher than 1. Now if you have a look at this ratio, let's say I'm going to start with this ratio. Between the speed of air and speed of glass, between these two numbers, which number is supposed to be bigger as per your understanding?
Glass.
Air.
Which number this is speed of light in air, this is speed of light in glass. Between these two numbers, which number is supposed to be bigger? Speed in air is supposed to be bigger, which means that if you do the ratio of these two numbers, this ratio should definitely be what? Bigger than 1, right?
Yes, sir.
It's supposed to be bigger than 1.
Yes, sir.
Similarly, if you look over here
Sir, which one? Air.
No, not air, the ratio value of these two numbers, the value of the ratio of CA versus CG, because numerator is bigger than the denominator. So if you do the division, this number is going to be bigger than 1. How big, that I'm not telling you, but it's definitely going to be bigger than 1. That's what I'm trying to state.
Yes.
Yusuf, you just asked a question, I'm responding to you. বুঝাচ্ছে?
Yes. Yes, sir.
So at the same time, if you look at this expression, what do we have over here? Sin x by sin y. What does this expression essentially mean? This means one sin ratio divided by another sin ratio. Now you have to understand one thing, that these optical angles, incident angle, refraction angle, these angles that we work with, they can never be bigger than 90 degree, can they? The limit is up to 90 degrees. So if I try to draw a very simple graph of sin ratio, let's say here is the, I might not as well draw here, I might as well zoom this a little bit. This doesn't work as a mobile screen, that I cannot squeeze the whole screen by diagonally pinching my fingers. Okay, I hope it worked. Might as well, I'm gonna become used to this. I mean, I just have to struggle a bit through the beginning. I mean, I cannot expect it to be an expert to use this in the very first go, but I think it's not that bad for a first class. At least I'm taking class, right?
Yes.
So the second thing that I want you to understand, that for this ratio of sin x by sin y, if you consider for this ratio, if I try to draw the sine curve for a very simple sine curve, let's say here I have the sine theta, and on the x-axis we have the theta, which is plotted in degree. And if I just plot this graph up to 90 degree, we are gonna get this shape, right? So the reason I'm trying to show you this shape is to give you an idea that within 0 to 90 degree, smaller values of theta gives smaller value of sine theta. So the bigger the angle value of theta is, the bigger will be the ratio value of sine theta is. But if you consider beyond the 90 degree part, in that case situation gets a bit difficult, because for this part 90 to 180 degree, bigger values of theta would give you smaller values of sine theta. Am I correct? Because what happens beyond this point? The graph starts to go down. ठीक ना? So for this region, 0 to 90 degree region, the bigger angles values of theta gives you bigger values of sine theta. Not essentially proportional, because this is a trigonometric ratio, but more, less. That is maintained for this region. Now try to have a look over here. This ratio was labeled as sin x by sin y. Take a good look at this figure. Logically, between this angle, this is the lighter medium or faster medium, this is the denser medium or slower medium. Between these two angles, which angle is supposed to be bigger? By all means,
The lighter medium, air.
Air angle is supposed to be bigger, which means x is gonna be always a bigger angle and y will always be a smaller angle, which means in this ratio, sin x will always be a bigger number compared to sin y. Both of these numbers are individually smaller than 1. Don't get my information wrong. But let's say if this is 0.5, this might as well come 0.3 or 0.45 or 0.4. But this denominator will always be smaller than the sin x value. See if you can make sense out of it. Because the x is bigger than y, so sin x is also bigger than sin y, which means the ratio of these two numbers, if I'm gonna do the ratio of these two numbers, the numerator is always going to be bigger compared to the denominator, once again the ratio of this whole thing is going to have a value bigger than 1. Now does that idea make sense?
Sir,
স্যার আপনি সেকেন্ড ইকুয়েশন দেখালেন না স্যার?
হ্যাঁ বলো, শুনতেছি।
সেকেন্ড ইকুয়েশনে তো উল্টাটা হয়ে যাবে, মানে ডিনোমিনেটর বড় হবে আর নিউমারেটর ছোট হয়ে যাবে নাকি?
You're absolutely correct. Second equationটা একটু পরে আসতেছি, but what you just said is absolutely correct.
sir,
It's going to be exactly vice versa for the second equation. হ্যাঁ বলো।
sir, sin 90 এর ভ্যালু তো 1 তাই না?
Yes.
So all the ratios will be less than 1, right? 0.00 something. It should be, because maximum is 90 degree.
Yes, logically speaking, yes. Logically speaking, yes, because there's a reason for this. I wanted to actually take the discussion of 90 degree when I plan to talk about the critical angle thing. I'll cover more information about the 90 degree part when I reach to the critical angle part, which is gonna come about, let's say, 20-25 minutes later. But I'll definitely answer your question. For that time, I mean, 90 degree part question ta skip kortesi for them.
Okay, but greater than 1, sir, ওটা কি বলতে যাচ্ছেন আপনি?
Oh, the greater than 1 বলতে বোঝাচ্ছি the ratio of these two values. None of these individual values will be bigger than 1, but if you do the ratio of these two numbers, this will always be bigger than 1. For example, so this number will be smaller than 1, this number will be smaller than 1 as well. But if you compare between these two numbers,
Yes, okay, thank you.
বুঝা গেছে?
Yes.
And vice versa for the lower equation. Have a look at the lower equation and see if you can make sense. I'm just going to write over here less than 1, and I want you to ask me questions if you have any question from this part. This expression is going to be very useful for you in the sense that you can always get your maths absolutely correct if you understand how this whole thing works. A statement মনে রাখতে পারলে, if you can remember this statement, you will never mess up your refractive index calculations. I mean never. So if you see, everyone have a good look. If you have any question over here, check this out. If you don't, then we're gonna move on to the next idea.
Sir, আমরা basically বলতে পারি না যে if the medium of which we are calculating refractive index is less dense, it is less than 1. More dense, more than 1.
Compared to the other one, yes.
So second equation
compared to the other one part
compared to the other one both means, I mean, if you're using the term comparative degree, for example, less dense, more dense, it's a comparative degree, right?
Yes, sir.
So if you want to use that term, you have to have something to compare. Something has to be bigger than other one. So what is the other one?
Yes,
compared to the other one. That's why I use that part.
That means if I try to compare air and glass, air is less dense compared to glass.
Yes, exactly. That's exactly
understood, sir. Thank you.
হ্যাঁ, শিওর। মুনাম কি বলতেছিলা?
সেকেন্ড ইকুয়েশনটা নিয়ে বুঝতে পারিনি, সেন্স বানাচ্ছে না যে কেন এগ্রি হবো, এটা বুঝতে পারিনি।
মানে কোন পার্টটা বুঝো না বলো?
যে কেন নিউমারেটর ছোট হয় ডিনোমিনেটর থেকে, এই পার্টটা বুঝিনি।
সেকেন্ড ইকুয়েশনের নিউমারেটর বড় হবে। Second equation just the reverse expression of this one. Here we try to measure the refractiveness of glass. So everything that belonged to the glass went to the denominator side. Here we try to measure the refractiveness of air. So everything that belonged to the air went to the denominator side. That's why now the ratio of this value would be less than 1. Ratio of this value will also be less than 1.
Okay.
Yes.
Sir, refractive index angle গুলোকে কিভাবে এফেক্ট করে, লাইক মোর বেন্ডিং অর লেস বেন্ডিং এমন কিছু আছে?
Now the angles are always affected by the speed of the light. The faster medium has bigger angles, and the slower mediums have smaller angles. But the question that you ask, kibabe affect kore, I mean, you are more inclined towards the why that happens, which is not discussed in your syllabus. But I can tell you this after the class if you're interested. Yes,
sir.
So I'm moving on from this part. So we're gonna get into the idea of critical angle at this point. So let me write this part. So now we are getting to the idea of critical angle and TIR. লেখা যায় খুব ভালো, ড্রয়িং করতে গেলে ডিফারেন্ট কালার চুজ করতে গেলে একটু প্রবলেম। এটা আমার আয়ত্ত হয়ে যাবে, সমস্যা না। I'll be okay with the zooming in and zooming out effect as well.
তো স্যার রিফ্লেকটিভ ইন্ডেক্স মিন করে যে কতটা অ্যামাউন্ট কমবে মানে এক মিডিয়াম থেকে আরেকটা মিডিয়ামে যাওয়ার সময় ওই ভ্যালু রিপ্রেজেন্ট করে না?
Yes, exactly. Physical significance is that how much will the wave slow down or speed up, which essentially also affect its direction. Munaim, just because you asked this question, what I can also elaborate further, let me draw over here. So let's say to explore the proposition of Munaim, what I can also show you. Let's say we have two different cases where here was air and here was glass, and let's say here was air and here is water. Okay, let's say for this glass, let's say the refractive index of this glass medium is given as, let's say, 1.8, whereas the refractive index of this medium for water, this water is, let's say, 1.4. So they have different refractive indexes. So what is essentially true, if you send some light ray with equal incident angle for both the cases, let's say you're gonna shoot inside this medium an incident ray at 60-degree incident angle, and you're gonna do the same thing over here. So two rays are falling onto the surface at 60-degree incident angle. Let's say that is happening. Whenever this will happen, the one that has a higher refractive index will make the ray bend more, which means for this medium, the refraction angle, let's say if this angle is, let's say, theta g, and let's say this refraction angle over here is theta w, you can essentially understand that this will bend more, this will bend comparatively less, because this has a lower refractive index. So I can logically write the value of theta g should be smaller than the value of theta w, because this would bend more, this would bend less, which means this would become more closer to the normal, this would become closer to the normal, but not as much as this one. Both of them would bend closer to the normal, but this would bend more, this would bend less. See if you can appreciate this information regarding on these two values.
তাহলে যদি আরো মানে লেস রিফ্র্যাক্টিভ ইন্ডেক্স হয় তাহলে নরমাল থেকে আরো বেশি দূরে সরে যাবে।
Yes, it will definitely get closer to the normal. That's always true, because for both the cases, the starting medium was air and the entry medium was something denser than air. So both of my cases, the light rays are going to bend closer to the normal, but more dense mediums would make them bend more, which means they're going to get more closer to the normal for more dense medium, and vice versa for less dense medium, they would bend less closer to the normal, but they're still going to bend closer to the normal. They're not going to bend away from the normal. They're still going to bend closer to the normal, but how much is that bending? That's what I'm trying to get at. Or in other terms, I can tell you, let's say if this was the original track of the incoming ray, and this was the original ray of the incoming ray, this angle is going to be more, and this angle is going to be less. So this will be bending more, this will be bending less. That's another way to visualize that.
Sir, higher refractive index, lower refracted angle.
Yes, because once again, if I add the equation, sine 60 divided by sine theta g, this is supposed to be 1.8, whereas over here, sine 60 divided by sine theta w, this is supposed to be equal to 1.4. Both of these sine 60s are equal, right?
Yes.
So if this number has to be bigger, obviously this number has to be smaller compared to that one. I mean, between these two, if you compare this between these two denominators, the denominator that produces the larger value should be smaller compared to the denominator that produces the smaller value. The denominator that produces a larger value should be definitely smaller compared to the, if you, I mean, এই দুটো নাম্বারকে রেশিও করে 1.8 আর এই দুটো নাম্বারকে রেশিও করে 1.4 আসছে. So if you compare because the numerators are both of the numerators are perfectly equal to each other. Please, internal কথাবার্তা বলতে হলে চ্যানেল মিউট করে কথা বলো, whoever you are. So because both the numerators are perfectly equal, so the only reason we can have different values of those ratios is because of the denominator. So j numberটার ratio value বড় হবে, the number the ratio value is bigger, that must be, for that case the denominator should be smaller. Very simple example. Let's say if you divide 5 by 2, you're gonna get 2.5. If you divide 5 by 3, you're gonna get what?
More smaller.
1.666. 1.666.
More smaller number.
Nah.
2.3.
2.3. Nah, 2 to hobe na.
So 1.6.
1 point something হবে এটা sure.
1.666, 1.67 for example. So that's something that's easier for you to compare. That if the denominator is smaller, then your result is bigger. If your denominator is bigger, then your result is smaller. So that's what I tried to show you over here. So for the question that you just asked, that the denser the medium, the smaller is their refraction angle. That is absolutely correct, provided we have given them same incident angle.
Okay.
Yes,
Yes, sir. Yes, sir.
So this one goes away. Coming to the idea of critical angle and TIR. Okay, the first concept that we want to consider for critical angle is that, let's just give you an idea for critical angle. So I might as well try to copy some image from the net.
Sir.
Easier for me to work. Bolo.
Sir, এমন কোন ইকুয়েশন আছে যে রিফ্র্যাক্টিং ইনডেক্স বের করার জন্য যে স্পিড অফ লাইট ইন ভ্যাকুয়াম ডিভাইড বাই স্পিড অফ লাইট ইন দ্যাট মিডিয়াম?
বলো আর বলো।
আর এমন কোন ইকুয়েশন আছে যে রিফ্র্যাক্টিভ ইনডেক্স বের করার জন্য আমাকে স্পিড অফ লাইট ইন ভ্যাকুয়াম ডিভাইড বাই স্পিড অফ লাইট ইন দ্যাট মিডিয়াম?
হ্যাঁ,
স্যার ওখানে তো লেস দ্যান 1 হয় না।
Because vacuum is always the lesser dense medium compared to any other physical medium.
Oh, আচ্ছা।
This is a good one. I hope I can paste this over here. And I hope I can make this longer. Well, this is not a very high definition image. This is amazing. Should I take this one or this one? Or this one? Oh, this figure. Hold on, which one do you like more?
The one which will give a high resolution image.
This one is better.
Answer.
So we can zoom as much as we want, so it's not a big deal, I believe. Okay. This will do my purpose. Everyone, have a look and try to appreciate what is being shown in this figure. Try to appreciate this one. Have a look. What is happening? We have a light source over here, and although this light source is aiming upwards, but let's say we are going to rotate this light source in different angles to make certain light ray go in different angles. So you can see over here that it's very important for you to understand that in this case, the light source is placed inside the denser medium. So here is water, here is air, here is water. Air has a refractive index of 1.00 because we consider air and vacuum to be equal, or they are considered to be replaceable. So in vacuum, the speed of light is considered to be 310 meters per second. In air, it is also considered to be the same. So that's why air has a refractive index of 1, which is to vacuum, and water has a refractive index of 1.33. So water in this case is the denser medium, and air is the lighter medium. Now the light source was placed inside the denser medium. This is a very important fact. You can only get the idea of critical angle only when the light source is inside the denser medium. I'll explain why this is gonna necessary in a bit. So if we send the light ray vertically upwards, then this is gonna go out vertically upwards. Now you can see over here, in this pathway, we do not have any bending. Do we have any bending?
No, sir.
No.
We don't have any bending. But if I ask you, well, there is no bending, so there is no refraction. Would that be correct?
Because there's change
No,
in speed.
sir.
No, sir.
No, sir.
Change in speed.
Change in speed.
Exactly. Refraction is not essentially the change in direction. In the definition of refraction, we usually define refraction by means of the in the definition of refraction, we use the term of bending to make sense of the refraction, but it is not essential that change of direction must be there, because for this exclusive case, when the light rays fall onto the boundary of the two medium at 0° incident angle, then it is gonna go out at 0° as well. In this scenario, you will not have any bending, but you'll essentially have speed variation. Whenever the light rays entering into the air medium, coming in from the water medium, it will definitely speed up. So one more thing that I actually forgot to show you in our earlier figure, for example, in this figure, if I try to do this, for example, let's say, if I want to draw the wavefronts, I might as well try to draw at least few wavefronts over here like that. Let's say here the wavefronts are labeled like this, equidistant parallel lines. Okay, let me draw. Acha, drawing.
আমার নেটওয়ার্কের সমস্যা হচ্ছে তো, একটু আবার কথা একটু বলতে পারবেন?
We are trying to show the wavelengths over here by drawing the wavefronts of the light rays. So
okay, sir,
if in the air medium we draw the wavelengths or wavefronts to be this much, in this case the gap between consecutive wavefronts represents one wavelength. So for example, over here this much is 1 lambda. So this is the lambda inside air. Okay, and as the wave enters into the glass medium, we can also draw the wavelengths over here. But if I try to draw these wavelengths over here, these wavelengths are supposed to be what? Smaller or bigger? Tell me.
Are smaller.
Smaller.
As the exactly, because the speed inside the glass would be smaller. So in this case, I need to draw them visibly smaller compared to those. And these lines also have to be parallel with each other, perpendicular to the direction of the light, and has to be equidistant. যেমন এখানে আমার লাইনগুলো equidistant হয় না। equidistant হয় না কারণ হচ্ছে I messed up the third line. Can I select the third one explicitly? Yes. Can I move it a little bit? No. Can I move it slightly? Can I move it slightly? No. So I might as well delete that and try to draw another one. Let's say over here. So from okay. So this is one way to represent the wavelengths as well on the same figure. So this is also a very important bit for us. So this is another part. So coming back to the same figure that we are discussing, that if we send the light rays over here, if I try to show the individual wavefronts over here, just showing you the wavefronts. If these in the water medium, if the wavefronts are shown to be closer, in the air medium, these wavefronts have to be shown to have a further gap. So that's basically what she's showing, that refraction is happening. So as the wave enters from water into the air medium, it does undergo speed variation. Someone raise their hand. Who is that? Or not? Sadman Yusuf, তোমার চ্যানেল থেকে খচর মচর শব্দ আসতেছে, ব্যাকগ্রাউন্ড সাউন্ড আসতেছে। If you're not asking the question, if you're not asking the question, make your channel muted and don't make it auto delete the sound. Yes, bolo. আচ্ছা। So this is gonna happen. Acha, let's continue further. এখানে দেখো, if we now tilt the light source a little bit so that the light is gonna send at, let's say, 20° incident angle, then in this case, by using this ratio, they have calculated out these angles. They have found out that in the air, the air angle is gonna be 27°. When you send the incident angle 30, 42, 40, 59. Then there is a very specific angle value. I mean, we are now slowly tilting the source to make the incident angle bigger. So each of these, so here the incident angle was 0°, here the incident angle is 20°, 30°, 40°, and there happens to exist a very specific angle for which this light, have a look, this refracted ray is slowly slanting closer to the surface. Do you see it? This is vertical, a bit more slanted, a bit more slanted, a bit more slanted, and there exists a very specific value of the value of the incident angle inside the incident angle inside the water medium, for which the refraction angle on the air medium can become 90°. Check this out, this way, this one. This is the ray that is giving us the critical angle. So critical angle is called this angle. Have a look at this labeling. Hold on, I was being extremely annoyed by the gudur sound coming in from your backgrounds. So I muted you all. If you have any questions, you can raise your hand and wait for your turn. So have a look. So what I'm trying to mean that this angle that is happening inside the water medium, there exists a very specific value of the incident angle inside the water medium, for which the refraction angle in the air medium can be 90 degree. This incident angle is what is being called the critical angle. This is the important bit that you have to understand. The definition of critical angle goes like this. Listen up very carefully. I'm going to say the definitions slowly, and the notes likha ase, so I likhte na. So listen up very closely. When light waves are traveling from denser medium to a lighter medium, when light waves are traveling from a denser medium to a lighter medium, or you can also write when light waves are traveling from a slower medium into a faster medium. Either of them will work. But don't write slower and denser and faster, or don't write lighter and slower. So that would be a bit confusing. If you're trying to differentiate them in terms of their density idea, then you write denser and less dense, or rarer, denser and lighter. If you either use those pair of words, or you use faster and slower, those pair of words, either of those. So let's say, so I'm starting again. When light rays travel from a denser medium into a lighter medium, the value of incident angle inside the denser medium, for which the refraction angle inside the lighter medium becomes 90 degree, is called critical angle. So the critical angle is not the refracted angle. Critical angle happens to be the incident angle inside the denser medium. I'll say it again. When light rays travel from denser to lighter medium, the value of incident angle inside the denser medium, for which the refraction angle becomes 90 degree inside the lighter medium, is called the critical angle. Now, so there is a small bit of alteration that we can make to this definition. You need to also understand the alteration as well, because MCQ questions can come from any of this aspect. That alteration is that the question can also, mentioning that the refraction angle becomes 90 degree can be also be explained in the using the phrase that when the refracted ray passes along the boundary of the two media. Medium e plural hoche media, not mediums. So the definition can also also be written in this fashion. I'm saying the definition once again. So try to distinguish the difference compared to the earlier one. When light rays travel from denser medium into lighter medium, the value of incident angle inside the denser medium, for which the refracted ray passes along the boundary of the two media, is called the critical angle of the denser medium. Critical angle belongs to the denser medium. Critical angle doesn't belong to the lighter medium, because you can see over here that where was the critical angle produced? Inside the denser medium. So that's the whole idea of critical angle. Critical angle একটা খুব বড় implication হচ্ছে. If I just look it from over here, this is air and this is water. So if I try to write the equation of the refractive index of water, let's say refractive index of water can very well be written as sine 90 divided by sine C. Critical angle is symbolized using the small letter C. So I can write this. Now the value of sine 90 is by default 1, so I can write 1 by sine C. So it's 1 by sine C. So this is a very important information, that refractive index of any medium can be written as 1 by sine C. This is important because you might have a lot of paper 2 questions, or quite some good number of MCQ question where you might be provided with the refractive index value. You might be asked to calculate the critical angle, or vice versa, which means that you might be provided with the critical angle value. You might be asked to calculate the refractive index value. So that might also happen for us. So that's the implication for the critical angle. 2 points you have to remember. Critical angle exists inside the denser medium, not the other way around. Now, why does it have to exist inside the denser medium? Why could it not happen in the lighter medium? Let me explain that part, which is a bit additional thing. So I'm gonna go over here to explain this. Try to understand. It is imperative for you to understand that whenever light rays travel from denser into lighter medium, light rays enter at a bigger angle. Let's say this is the normal. Light rays enter at a bigger angle, and light rays pass through. The incident angle is always bigger, and the refractive angle is always smaller. So let's say you start to send the incident ray at over here. So if I send the incident ray, let's say I'm gonna draw with blue over along this line, then this is gonna be my incident ray, and this is gonna be my refracted ray in the same path. No big deal. Then if you slowly start to tilt it, if you slowly start to make the incident angle bigger and bigger and bigger, you're gonna also slowly gonna start to make this refracted ray go farther and farther out and even farther out. You can do this, make this happen. But no matter how big you make this angle, this will never become 90 degrees. For example, if you slowly keep on making it bigger and bigger and bigger, hypothetically speaking, the biggest angle that you can make X into can be 90 degrees. Now you might wonder, why am I using the word hypothetically? I'm gonna answer this question in a bit. Let's say if I send now the incident ray along the surface and somehow make sure it hits the boundary over here. Now, why would that happen? There is a bit of a discussion about this thing, which Fardin just asked, which I'm going to explain. Then I'll take your questions if you have any. If we can somehow send the incident ray along the boundary and somehow make sure that it hits the medium boundary at this location, it's going to come into at some specific angle. So you can have the larger angle 90 degree, for which the smaller angle can be this. So important point for you to remember that the lighter medium will always own the bigger angle, and the denser medium will always own the smaller angle. So if you are trying to get the maximum angle for an optical scenario, which is 90 degree, that will always belong. আমি এখানে ভুল লিখছি, বলো তো কি ভুল লিখছি? আচ্ছা বলা লাগবে না, আমি কারেক্ট করতেছি, দেখলেই বুঝবা। Yeah, Sabir, thank you, and Takiya says thank you. I messed up, but yeah, I think I made sense. এখন ঠিক আছে কিনা দেখো। I believe so. So a situation to have. So this is what I wanted to appreciate, that what I want you to understand, that the 90 degree can only exist inside the denser medium. So a scenario you might wonder. So this is basically the exact opposite figure from compared to what we have seen over here. Here the light rays were sent from inside the denser medium. It was hitting the surface at critical angle, and the ray was going along the boundary. And here and what I showed over here, that light ray was being sent along the boundary, and it hit the surface over here and coming down over here. Now you might wonder, how is it even possible if you shoot an array that is perfectly along the boundary? Why should it even hit the boundary at any point? Shouldn't it supposed to go straight forward along this straight horizontal boundary? Well, that is definitely what is supposed to happen. But I am showing you this collision using the idea that maybe this angle that we have over here between the incoming ray and the medium surface, this angle that we can have over here is extremely small. It is so small as to be negligible, but it's not exactly zero. যেমন একটা এক্সাম্পল তোমাদেরকে আমি দেখাই, একটা এক্সাম্পল আমি তোমাদেরকে দেখাই, যে এক্সাম্পলটা বললে তোমাদের জিনিসটা আর একটু ক্লিয়ার হতে পারে, because I'm picking up this reference. Oops. I'm picking up this reference from an actual question, so might as well go there. Consider this equation. Check this out. Figure 9.1 shows a young boy lying on his back on the bottom of a swimming pool. He is holding his breath and his eyes are open. I have no clue why would anyone try to do that, but CIE wanted this thing to happen, so the kid is following their orders, maybe, whatever. A red light is positioned on the ground at Q. At first, the boy's head is touching the pool wall. So initially, the boy's head was here. He notices that as he slides away from the pool wall, his eye reaches a point P where he first sees the light at Q. Figure 9.1 shows the boy in this position. Then it says on figure 9.1, draw the ray of light traveling from Q to P, mark the critical angle for light in water and label it C. Now, I'm going to show you how to work with this thing so that I can make sense with you. Can I paste it over here conveniently? I hope I can. Such a small figure. What if we try to, wow, it maintains its okay. So now the question says that the boy was initially here and he couldn't see the red light source being under the water. He was slowly moving further away, and this is the first position where he could see the red light, which means this is the point where the red lights could somehow bend to his eye. So the most logical drawing that we could possibly do in this case, image menu, add note, add text, lasso select, ruler. Okay, this is an indefinite ruler. How can I change the ruler's orientation? Oh man. Acha, disregard that. রুলার ইউজ আমি আমার পার্সোনাল টাইমে শিখবো, ক্লাসে আমি টাইম ওয়েস্ট করতে যাচ্ছি না। আচ্ছা, আমি নরমালি একে দেখাই, তোমরা একটু আমার সাথে বোঝার চেষ্টা করো। If you have questions, raise your hand or ask the questions in the chat window, don't worry. So let's say the light rays, let me draw with red. Let's say the light rays are gonna come through here, and these light rays are actually spreading out in all directions. Some light rays are gonna fall onto this water surface. So it's possible that light rays, you see this light source is not essentially underneath the surface. It is slightly above this surface, slightly above. So if I try to draw a straight line from the center of this light source all the way to the very first corner of the medium over here, between these 2 points, if I try to draw a straight line, which I'm gonna try and draw, not a very perfect line, but works. You can see over here that this angle between the light ray and the actual air water surface, this is extremely small. So hypothetically speaking, we can consider this angle to be negligibly small. So let's assume that this theta is approximately 0, but it cannot be exactly 0, but because if it was exactly 0, then the light ray is never supposed to hit the water surface. So the light ray should fall through this corner, and through this exact corner, exactly from the corner, the light ray should reach to the kid's eye. So I might as well try to draw a straight line as best as I can, like that. So this should be the path of the light rays. In this case, the light ray is entering from the lighter medium into the denser medium. But as the definition already tells us that whenever, I mean, like I said, that the denser medium will always hold the smaller angle, which is the critical angle, and the lighter medium will always hold the 90 degree. So if I assume that this angle is perfectly 90 degree, this angle by definition is supposed to be what? critical angle. Critical angle. So it can also happen. I mean, for a practical scenario, we can also have a situation like this, where the critical angle might also be possible to achieve when the light rays are traveling from the lighter medium into the denser medium. But in those cases, that incident angle should be considered to be approximately 90 degree. It shouldn't be exactly 90 degree, because if it is supposed to be exactly 90 degree, the light ray should never hit the surface. So this angle that it would be short by would be considered to be negligible. That's a simple scenario that we have. So we're gonna use this logics over here to solve this question further on. So if you have a look over here, explain why the boy is unable to see. Explain why the boy is unable to see the red light when his eye is closer to the pool wall than P. So when his eyes were closer to the pool wall, the light rays could not. The smallest angle at which the light rays could bend into the boy's eye is the critical angle. So the closest the light rays could reach to the pool wall at the level of the boy's eye level, was at this location. So light rays cannot bend at a bigger at a smaller angle as they enter from the air medium into the water medium. That's not gonna work out. So that's one of the reasons that he cannot see it over. এটা ভাষাটার সাথে গুছিয়ে লিখতে হবে. Then it said the critical angle is 49 degree, calculate the refractiveness of the water. এখানে যে calculate the refractiveness of the water যে আমাদের calculate করছে, এটা calculate করার একটা simple উপায় হচ্ছে এরকম. We can try to do this calculation that n equals to 1 by sin 49. So you can very well go ahead and calculate this value, which is going to be perfectly work out for you. And we can move on forward. It further says the red light is now replaced with a blue light. State the effect this has on the wavelength of the light in the air. So if you compare the wavelength series between red and blue, which one has a bigger wavelength? Right in the chat window. Between red and blue, which one has a bigger wavelength? Red has a bigger wavelength and the blue has a smaller wavelength. Exactly. So the question says the red light now replaced with the blue light. State the effect of this on the wavelength of the light in the air. So simply the speed would be very much same, because C is same for the same medium of air. All the electromagnetic spectrum has the same speed. So whenever you increase the, so whenever you will so wavelength would be, so you are just going to write wavelength becomes smaller, or you can simply write decreases. Single word, decreases, scores you the mark. Good enough. Because the question says the effect of this on the wavelength of the light in the air. So what happened to the light in the air when you replace it? The red was replaced with the blue. The wavelength decreased. So you just write decreases. Single word, enough. So let's just move on to the back to the question. So I'm gonna allow you to ask questions. Fardin to হাত উঠাও. Where's Fardin? Yeah, okay. Yeah, Fardin, you are unmuted. So I would like you to interact with you. You asked me a question about the 90 degree thingy. So this is the part of the 90 degree discussion that I wanted to go by. That whenever you are sending light from inside the denser medium into the lighter medium, you can have a perfect 90 degree, no problem with there. But whenever you're trying to send the light from the lighter medium into the denser medium, then that incident angle should be approximately 90 degree, but it cannot be exactly 90 degree, because exactly 90 degree would mean the light rays should never hit the surface. Did this idea get passed across? Could I answer your question that you asked me earlier? Hello. Acha. So yeah, I'm turning on the unmute options for everyone. So if you have any question, respond one by one. Any questions so far up till this part?
Number 2 টা আরেকবার বলবেন.
Number 2, a answer ta.
Yes sir.
I can essentially show you the mark scheme. Did you understand the logic for this? That light rays should bend over here, and the smallest angle by which it can bend is the critical angle. Smallest angle মানে হচ্ছে এর চেয়ে ছোট অ্যাঙ্গেল এত bend করতে পারবে না, because it has a very
critical angle is that.
Exactly. That's why it is going to be reaching up over here. So I can show you the mark scheme, which might give a bit of a better idea. This is question number 23 of the light worksheet. So if I just pull out the mark scheme.
স্যার এসেনশিয়ালি যদি আমাদের পি এর কম একটা অ্যাঙ্গেল দরকার হতো, তাহলে তো আমাদের 0 ডিগ্রি নিচে থেকে ইনসিডেন্ট অ্যাঙ্গেলটা মারতে হতো, which is not possible, right?
Not possible, because in that case, the light ray would not hit the surface if I consider it to be exactly 90 degree.
Yes, sir.
So we have to assume it to be approximately 90 degree, slightly smaller, that much smaller that we can consider to be almost 90 degree. So it is practically 90, but not exactly 90 for the experiment to work out. Have a look at this explanation. They have given you the explanation over here that for I equals to 90 degree or horizontal ray, angle in water equals or cannot be less than critical angle. Okay, that's basically the idea. So they have mentioned the initial angle first, that for I equals to 90 degree or for a horizontal ray, you have to have that pre logic that for this much angle, the angle in the water cannot be less than the critical angle, or it equals to the critical angle.
Cannot be less, therefore it cannot be seen.
Exactly. Or we can also look at the examiner's report a bit so that we can make a bit. Very few totally correct answers were seen. Exactly. Why not? Very few totally correct answers were seen. Candidates did not realize that for an angle of incident of 190 degree, the angle of reflection in water cannot be less than the critical angle, and so the boy is unable to see the light if his eye is any closer to the pool wall. So this one basically gives us a very good structure of sentence. If you want to write it into sentence, you can just convert these sentences into direct sentences to make your answer work. That works, I believe.
Sure.
Yes. এক মিনিট হ্যাঁ আব্দুল্লাহ বলো, তারপর বাকিদের কোশ্চেন এসে বাকি হাত উঠে রাখো। হ্যাঁ আব্দুল্লাহ বলো।
অ্যাঙ্গেল অফ ইনসিডেন্স না ক্রিটিক্যাল অ্যাঙ্গেল হয়।
That's what I said for you to understand for two different scenarios. That here for the definition we decide we define the critical angle to belong inside the denser medium. That is when we define the property, and for definition we always define the critical angle as if the light rays were traveling from the denser into the lighter medium. But it is possible for situations like this, the critical angle might also exist when light rays are traveling from the lighter medium into the denser medium. But then again, the critical angle will always be produced inside the denser medium, inside water. Bucho?
Yes, sir.
Acha. Okay. Yes, Yusuf.
Sir, you said that if the red light is reflected the blue light, the wavelength will decrease. I mean, will the boy still be able to see the light rays at the position P, or something else will happen?
Acha, this is a very good question, which I'm gonna discuss. I'll be able to answer your question after a little bit when I get into the idea of prism. So I'll be able to explain that. But I'm holding this. I'm keeping this question on hold. I'll answer this in a while. Chandrima.
Sir, a case so the critical angle is not the incident angle.
No. For this case, critical angle is the refraction angle.
Sir, critical angle definition কি আমরা incident angle টা mention করব যে it
Yes.
is the incident angle.
Yes, because the way we define the critical angle goes like this: that whenever light rays are going from the denser into the lighter medium, the incident angle inside the denser medium, for which the refraction angle inside the lighter medium becomes 90 degree, or the reflected ray passes along the boundary, is the critical angle. That's how we define this thing. But vice versa, I mean, think about this: if the light ray go along this line and eventually goes along this line, logic tells us that the opposite should also be possible. But physically speaking, opposite should not be possible, because if we shoot a light ray exactly along the boundary, why should it ever enter the water medium? It should travel along the boundary, period.
Yes.
That's why this idea of slightly smaller angle was required for us to appreciate. This is not an essential part for you to understand for the aspect of the question, but I explain this part to get you rid of the confusion that you might have had, to have a much deeper understanding for how this thing is relevant to this thing.
Yes, sir. Thank you, sir.
Sure. Rahma.
Sir, does reflection, refraction, and diffraction only occur for light rays?
No, they occur for all waves.
Okay, sir.
They occur for all waves. For example, refraction of sound is also possible, which is not actually a very common example that we have experience for, but it can be experienced for very large regions. There are some experiments which were included in the syllabus for 2 sessions, Then they discarded those experiments once again from the last session. So you don't have those experiments in your syllabus, but I'm gonna show you them because it's good to know. You never know. I mean, I feel like that something that they recently discarded from the syllabus might as well be within the shadow boundary of the syllabus. So I'll cover that part. But one thing I can tell you is that one of the other questions that we have in this worksheet in the general waves chapter, where we were working with some earthquake waves which were traveling through rock and some actual ground or soil. So there was a bit of a difference of the time measurement, which gave us some idea about the rock thing. Let me find this out. Hold up.
Sir, so they occur for all the waves in the spectrum?
So, yeah, just a second. I mean, you just asked that, just do they apply for all the waves? Here is the thing, that these people are trying to find out, let's say, where this layer of rock is located. So what they did, they made a very controlled explosion over here, and they put a detector over here. They measure this exact distance. This detector, at the first vibration that this detector will locate is wave number 2, because between air and earth, this vibration that will travel through physical medium is a mechanical wave. Mechanical waves have the property that in the air medium their speed is lowest, in the water medium a bit more, and in the solid medium the highest. So 1 is traveling through air, where 2 is traveling through earth, which is a solid medium, but the distance is very much same. So this detector will first detect 2. Then, logically speaking, because we don't have any value over here, positively thinking that then it should detect number 1, and then it should detect number 3. Do you get my point?
Shouldn't number 3 be detected as second?
Number 3 could also be detected at second, depending on these distances being too small or too large compared to the depth of the earth. That is also possible. I mean, between 1 and 3, either of them could be detected as the second wave. Because in the air medium, it will be traveling slowly. In the earth medium, it will be traveling. I mean, it all depends that how much time is required to cover the distance for the sound through the air medium, and also how much time does the vibration requires to be reflected off the layer of rock and back into the detector. So a path to cover the number 1. I mean, how much? I mean, we have to get a comparative idea. How much time does it take to cover the path 1 through air, or how much time does it take to cover the path 3 after the reflection to the layer of rock? So this can also happen. So you can see over here that in this case, for this scenario, we are having reflection for this path number 3. We're having refraction for path number 4. Have a look, earth into a layer of rock. Now you can see over here, if you consider this as a partial refraction, which actually happens, so which means that if whatever the amount of energy that we're sending down this path, a portion of the energy would be going back in this pathway, and another portion of the energy would be going up over there. So the energy is gonna get divided into 2 parts, not essentially equal parts, but 2 parts. So you can see over here, if I draw a normal over here, so if you assume a normal over here, so I might as well use annotation because I don't want to copy it to that part. So where is the annotation? Draw straight line. Okay. So let's say if I try and draw a normal over here, if you have a look, in this case, this is the incident angle and this is the refraction angle. Which is the bigger angle? Between this angle and this one, which one is the bigger angle?
Refraction angle.
Refraction angle.
The rock angle is the refraction angle, which means between the earth and the layer of rock is the faster medium. And we can also have reflection for this mechanical wave as well. So the question that you asked, that is it possible for those happens to happen to other waves than light? The answer is a solid yes. Yes. Ahma, yes. Do you have any further question?
No, sir.
Okay, yeah. Fardin, go ahead.
Sir, medium এর সাথে তো speed change হয়, right? Because wavelength change
Yes.
হয়. So sir, ওই যে red wavelength যেহেতু change হয়, তো red যখন when red will be replaced by blue, so blue এর speedটা একটু কমে যাবে না because wavelength change হইতেছে?
No. I'll tell you no for one reason. All electromagnetic waves have the same speed in vacuum or in air. So once you define the medium to be air, C is same for all the frequencies. So if you try to visualize or just have a look, you don't have to visualize. How can I? Okay, this is gonna be here forever because I might as well clear it. Okay. So what I mean is that if you have a look over here, C equals to F lambda. Whenever you choose air medium, then C becomes a constant for all the different parts of the electromagnetic spectrum. For gamma rays all the way through the radio waves, C is a constant value for all the entire electromagnetic spectrum in vacuum/air. So in that case, when frequency goes higher, lambda becomes smaller. But exclusively for air or vacuum, the speed of electromagnetic waves is same.
For a constant medium. Okay, sir.
For a constant medium, different choice of frequency will give you vice versa relationship with the wavelength. But if you send the same frequency light through different medium, then these equations are going to work out. For example, you send the blue light from air into glass, then you're going to work with these equations, because in that case the frequency would remain the same. So you have to take one variable at a time. Are you fixing up your medium and changing the different part of the electromagnetic spectrum? Then you're going to work with this equation where this will be a constant and these two will be changing vice versa, oppositely, inversely. But if you choose your frequency fixed, then these two variables, C and lambda, they will change proportionately.
Okay.
বুঝতে পারছি?
Yes, sir.
Okay, হ্যাঁ, সাকিব।
Sir, আগের ডায়াগ্রামটাতে like earthen layer of rock. Sir, ওখানে question ছিল।
বলো।
Sir, in that diagram, sir, is pathway 3 a total internal reflection?
No, pathway 5 is a total internal reflection. Pathway 3 is not, because you can see from the pathway of this light ray, part of the light ray is getting reflected, which we call partial reflection, and a certain specific part is also getting refracted. So refraction was possible over here, but refraction did not happen over here because no part of this vibrational energy entered into the lock layers. This would be to TIR. This one represents TIR, this one doesn't.
Sir, how did it both, or why did it both reflect and refract at the same time? Why not just one?
Because physically speaking, whenever a wave actually hits a certain medium, we always have both of the things happen at the same time. How much is going to be reflected and how much is going to be reflected depends on a lot of factors, which I'm not going to cover, not a part of a syllabus. But let me give you a simple idea, which might make sense. Water is a transparent medium, right? We know water to be a transparent medium. Let's say on a bright shiny day, if you stand beside a lake or a pond, you might as well see the reflection of the sun onto the water surface, right?
Yes.
Being able to see the reflection of the sun means light rays from the sun are falling onto the water surface, being reflected into your eyes. But water is a transparent medium, correct?
Yes.
So light rays will also enter into the water as well.
Yes, sir.
So 100% light that falls onto the water surface are not exclusively reflected or not exclusively refracted. It gets split up.
Oh, okay.
Thank
you. Yes, sir.
I did not essentially told you the reason why it happens. I gave you a practical example to make sense out of it. Just to be clear.
Yes, sir. Thank you, sir.
Sure, no problem. হ্যাঁ ফারদিন বলো।
স্যার ওই যে ইউসুফ যে কোয়েশ্চেনটা করছিল না যে যদি আমরা ব্লু দিয়ে চেঞ্জ করে দিই তাহলে কি রিফ্র্যাক্টেড অ্যাঙ্গেল বেশি হবে নাকি?
হ্যাঁ, you have the same question.
ওকে ঠিক আছে, থ্যাংক ইউ।
হ্যাঁ, ওইটা আমি একটু পরে আলাপ করতেছি। আমি প্রিজমটা একটু আলাপ করলে ওটা ক্লিয়ার হয়ে যাবে। ওকে, so that pretty much takes care of the question answer for this part. And then comes the idea of TIR, which is pretty simple, which is the very next situation after the critical angle. If in any case the incident angle inside the denser medium is bigger than the critical angle, then the light rays are gonna start to 100% reflected back from the inside boundary of the water. No light would be entering into the faster medium. All the light means 100% of the light would be reflecting back into the denser medium. This incident is what we call total internal reflection. The name itself says total. Total means total energy will be reflected. Internal means the reflection happens from inside the denser medium boundary. It doesn't even enter into the lighter medium. That's why we use the term internal. So total it means for the energy, and internal means from exclusively inside the denser medium, and reflection means this will not be reflected, this will be reflected. Reflected means in this case we're gonna have I equals to R. You can see over here as they are showing that for this figure, for this figure, the critical angle was 48.8 degree, and then they chose a random bigger angle which was 60 degree, and when they shot this way at 60 degree angle, then the light was bending all the way inside, which is 48.8 degrees. So this is actually a pretty good explanation for why this happens. I could show you a physical example for how a total internal reflection can be physically seen. I might try to show you right now as well. Yes. This is mind blasting. Do you have any idea what is happening here? Did you even understand what happened here? Have a look. This light is being shine upon over here, and as the light ray travels through here, I mean, there is a small tiny hole, and this laser light was aimed directly towards it. This is a not clear plastic bottle, and the refractive index of the water and the wavelength of this and the frequency of this laser light was matched in such a way that whenever the laser light hit the internal surface of the water stream, that incident angle was bigger than the critical angle. So it got reflected and bounced onto the inside over here. So it continuously got reflected on the inside boundary of the water. This is why the entire stream of the water is basically carrying out the laser light, and it is passing through over here. Eventually over here at near the end of the stream is breaking apart into drops. So it's not a continuous medium anymore. So the laser is coming out. So that's why the light is no longer visible over here. But as long as the water stream is maintaining continuum, the light is being contained within. Unbelievable. Did it make sense anyhow? Okay, I'll take questions. Yes. Fahim Abrar.
Sir, smarter everyday একটা total internal reflection video আছে।
I totally agree with you. I forgot about that. I'm gonna smarter everyday একটা ঝামেলা হইতেছে। I mean, আমি তোমাদেরকে একটা জিনিস বলি। In a lot of lectures, since I have started to upload a lot of videos, YouTube started to scrutinize me. All the YouTube videos that I played as a continuous video in my lecture, they put copyright claim onto these things. So I had to trim out those sections so that they do not take out my, they do not actually ban my channel. So they put a copyright claim on my video, so I had to trim out those sections. What I plan to do is that in the description, I'm going to give timestamps, and I'm going to provide the link that at this timestamp, there was a video of this link, which was removed due to copyright claims, so that kids who want to get a reference to that video, they can essentially click on that link and see that video for that reference of this time frame. So for those who have done classes with us, eventually when you will start to revise your lectures from the YouTube at any point, if you want to do that, you might actually come across a situation where a lot of the YouTube videos you might see that they are removed from from my lecture videos. This is because of the copyright claims. I don't want my channel to get banned or deleted by YouTube. So I removed all the copyright claims immediately I came across them. বুঝাচ্ছে? So smarter everyday video যেটা আছে গাজী, ওটা তুমি একটু সার্চ করে আমাদের মেসেঞ্জার গ্রুপের মেসেঞ্জার থ্রেডে সেই লিংকটা শেয়ার করে দিও. If anyone have any question, I'll definitely come across and do this. Okay. Yes, Aprodim, go ahead. You had a question. You can unmute yourself, or can you not? Oh, sorry. Yes, yes, you can speak now.
Sir, একবার TIR হলে কি ওটা বের হয় না?
Well, বের হবে, অবশ্যই বের হবে, কেন বের হবে না? For example, let me show you an MCQ example. Or maybe not an MCQ example. I mean, if we just go for TIR over here. Oh, come on. টিআই হলে অবশ্যই লাইট বের হবে কখন তোমাকে দেখাই। This is how essentially optical fiber works. That laser beam gets continuous. Asha, this is the water air. So this is the exact explanation of that thing. Soda can thing. এই যে টিআই, আচ্ছা এটা হচ্ছে তোমার একটা লং পাইপ homogenizing rod or whatever. So this is actually a way how the optical fiber work. We send the signal beam through one of the open surfaces on one end, and it continuously get total internally reflected through the internal border of the channel, and eventually it can be going out on the other surface. The idea is very simple. The moment the incident angle becomes less than critical angle, the light is gonna come out. But as long as the incident angles are more than critical angle, the light is gonna be continuously bouncing back and forth. Did I get your question answered? অপ্রতিম, বুঝে গেছে? হ্যালো, আচ্ছা, okay, thank you, thanks for the response. Drop your hand if you don't have any questions. আমাকে অনেক স্টুডেন্ট অনেক মেসেজ পাঠাইছে, ক্লাস শেষ করে তারপরে হচ্ছে আমার আবার কষ্ট করা লাগবে। অসহ্য আমি I don't want to manage these classes. আচ্ছা, কইছিলাম যেন আমি টোটাল রিফ্রেশন আপ করলাম। Okay, one more thing that I'd like to cover, and then I will call it a day. That is the prism thing. And although I have 2 minutes left, but I can actually try to work with it. Prism এর basic idea টা হচ্ছে এরকম. Let's say prism is basically a refractive medium which has 2 inclined surface. This can be triangular. This can also be trapezoidal as well. It doesn't have to be exclusively triangular. So if you have 2 transparent surfaces, so if a transparent medium has 2 surfaces which are not parallel to each other, you can use it as a prism, or that is a prism. So if you say rectangular glass block, then it will not have prismatic effect. For example, what happens in a rectangular glass block? Let me just tell you that about rectangular glass block, then I'll get back to the prism. If you have a perfect rectangular prism, rectangular glass block, and let's say you are going to send a light ray through this path. Let me show that light ray with blue. So if you're going to send a light ray through this path, what's going to happen? Rectangular means these 2 surfaces are parallel to each other. Let's say this is angle X, and then the reflection happens at angle Y. Oops. No. Okay. What is this? Okay. I'm sorry. So let's say this is angle X, and let's say this is angle Y. So by idea of alternate angle, this should also Y, and this should come out over here, and logic tells us that this angle should also be what? Angle X. ঠিক না? Wrong, দেখো. Do you make sense? Does it make sense? It should. So this means that whatever the direction of the incident ray was, if I extend this ray over along this line, this output ray and the incident ray would be very much parallel to each other. This ray and this pathway would be parallel to each other. The reason they are parallel to each other, because these 2 surfaces were parallel to each other. That's why these angles, 2 angles were equal. But this is not going to be so these 2 rays are going to become parallel to each other. This will be exactly angle X. So this is why these 2 rays are becoming parallel, but these 2 angles would not be perfectly parallel if these 2 surfaces were not parallel to each other, which is basically the case of what happens in a prism. So how the prism essentially work? I'm gonna delete this figure because I don't want to use this. This is how the prism works. If we send a light ray, and now I'm saying this light ray that I'm trying to show you over here is a monochromatic ray. Monochromatic means it has a single color. So just so that you don't feel confused with the color, I'm going to use a black light over here. So if we send a single color of or single frequency of light ray over here, I have a reason to show this light, send this light ray like this, because I'm going to show you multiple variation. Let me draw the normal over here. Normal is always normal with the surface, so I'm going to draw the normal over here. So whatever this angle is, this light is not gonna go in this alignment. It's gonna be slightly bent downwards. So I'm gonna make this bend happen. Let's say this light ray bends over here, and this light ray in this case is falling onto this surface with this much incident angle. And as it comes out, it's gonna make a bigger refraction angle, because it's now coming from air, glass into air. Eta to goal hoye gelo, goal to hobe na, straight line hobe. This is something like this. So this is my incident ray and this is my curved ray. So you can see that over here we have a basic differentiation of their angle. So the light ray actually did a significant bending as it traveled through here, and the bending would essentially happen twice. Once as the light ray enters from air into glass, then as the light ray leaves from the glass into air once again. How much is the angle of bending? How much did this light ray actually bend, or how much did it actually deviate from its original path? That can be found out easily by doing a bit of extension drawing. Let me draw that extension drawing using green. If I extend this incoming light ray a little bit in this direction and extend this output ray along this direction a little bit backwards, we can find out this angle. So this is the angle, what we say, the angle of deflection, which means if this prism did not exist here, this light ray was supposed to go exactly along this line and go forever. Because we placed the prism over here, now this light ray is going along this direction. So how much did it turn from its compared to its original direction? It turned by this much degree. Now the reason we had to do this extension drawing, because this light ray did not bend at a single point. The light ray did bend at two different points. That's why we have to extend this line backwards, and we can calculate this angle. This is actually a measure that how much bending would happen to this light. Now the question that you asked, that between blue and red, which one is going to bend more and which is going to bend less, this question I'm going to entertain right now. If I now draw a different figure over here, Abdullah, you have a question. I'm going to give you a floor, but let me just finish the part that I am trying to finish over here. So please hold your horses a little bit. I'll give you the floor, don't worry. So this is the case for a single monochromatic light or a light that has a single frequency. What if we send out a composite light? Let's say if we send out white light. So if we send out white light over here, this is white light. In that case, the white light, I mean, you don't, I might as well draw the normal, or you can skip drawing the normal. In many of the figures, you don't have to draw the normal, but I might as well draw. As the white light will enter this surface, it would split into its 7 colors, but all of them would bend towards the normal, which means these 7 color split you're gonna show, you cannot show any of them in the same alignment. You cannot show any of them to be going upwards. All of them would be below this line. So let me just draw a simple reference line to give you some idea. Let's say this is the original direction that in which the light was coming by. The entire 7 defined lights would be below this line. So you might as well draw only 2 of them. Drawing 2 of them is good enough, because you don't have to draw all 7 of them. Let's say I'm gonna only draw 2 of these with a little bit of deviation. And as they are gonna come out, both of them are not gonna go in the same direction. They are gonna bend downwards, because now these light rays are gonna bend closer away from the normal. So I might as well bend this in this direction and bend this in this direction. So what you have to show in your figures, importantly, that the light rays would bend from the original direction in the properly. And what you can do, the way this white light usually bends is that it bends into multiple parts. And if you are ever trying to draw this figure, you just have to label it like this. Labeling these symbols are good enough, but if there is a specific mark for writing all the names, you might also have to write the full names, but you don't ever have to draw 7 different rays. Don't bother to draw 7 different rays. The only reason we still stick to 7 different color of the rainbow is because Isaac Newton was a very renowned scientist. We honor him a lot. He was the first person who came up with this process of breaking up the white light, which is called dispersion. So and he said in his first observation that I could see 7 different colors, which are the colors of the rainbow. And we still honor his legacy by still naming them as 7 different colors. Whereas we human being came to understand that there are basically three different primary color, combining which we can make all the other colors, which you might come across to know from the printer color solution. For example, we can have RGB, red, green, blue. If you have these three colors, then by mixing them some appropriate percentages, you can make any of the color that we can get. Or in some other printers also work with CMYK. So CMY stands for cyan, magenta, yellow. So some printers also use these three color as their primary color. Combining them, they can give you any color. And K stands for black. Black is given by K, because we do not use B, because B went out for RGB এর blue এর B এর জন্য B খরচ হয়ে গেছিল, ওই জন্য black কে K দিয়ে represent করা হয়. So in some of the printers we have the color combination of RGBK, which means red, green, blue, which are the color printing options, and K stands for black. Or in some other printers also work with CMYK. They pretty much give out the same type of output, but different printing company works for different combination. I don't exactly know the reason why. I mean, whether one type of color variation has advantage of the other type of color variation, I really don't know about that part. But there are two of these defined color scheme that is followed around the entire globe. So that's the part. And the additional last thing that I'm going to cover for today's class, which I'm pretty late, but I really appreciate everyone to be sticking around. That is, if we ever send a light ray, let's say a white light ray, let's say not a white light ray, let's say if we send a monochromatic light ray that is perpendicular to the first surface. Let's say you are going to send a light ray. So if I send out a light ray that is perpendicular to the first surface, then what's going to happen? It is going to go from the first to the second surface undeflected. But as it reaches the second surface, it is going to come out bending away from the normal. So this is going to happen for a single monochromatic ray. And also, if this same thing is allowed for a composite white light, in this case, I'm going to prefer to draw my prism to be quite thin, so that I can draw this figure a bit comfortably. Let's say if we send white light along this line, because the incident angle is 0 degree, all the light would reflect at 0 degree, which means the spread out would not happen at the first surface. The white light will travel as white light to the second surface. Beyond this second surface, it's going to start to bend out. And how is it going to bend out? All the light rays are going to bend away from the normal, which means all the light rays that you are going to draw over here, all of them should be below this line. So you don't have to draw this hypothetical line, but I'm drawing this line to give you some reference. So I can essentially show one light to go like this, slightly downwards, and then another one slightly like this. You can essentially make them bigger as well. I'm showing you a little bit of bending over here. So I might as well show you V over here and R over here, and you can write all the other numbers over here. So one of the things that I want you to get your idea, that the question that you asked me a bit earlier, is that if you have a look over here, this is the incoming angle for the white light, and you can see that the violet is located at the most bottom, which means if you extend this backwards, violet would have bent the most, and red has bent the least. See if it makes sense. So the question that you asked, that if we send blue light and red light through the same, if we make them both of them to enter into glass, which one will bend more? Blue will bend more compared to red, because whenever light changes from whenever we send different frequency light rays into from one medium to another medium, the light ray that has a bigger frequency will always undergo the biggest amount of change. Bigger amount of change means whenever it travels from air into glass, it will bend more. Also, whenever it will travel from glass into air, it will also travel more. Now you might wonder that why in that case this is not compensating, because you have to understand both of these bendings are causing them to bend in the same direction. In this, have a look at this figure. As it was traveling from air into glass, it was bending downwards. As it was traveling from glass into air, it was still bending downwards. So both of this bending were making the light ray to bend downwards. So violet will bend more in this surface, it will bend even more on this surface as well. Combinedly, it will bend the most. Vice versa, red will combinedly bend the least. So that's the part of the discussion that I have had. I'll take one question from Ghazi Afahim Abra and then we'll call it a day. Yes, Abra bolo. Ghazi bolo.
Sir, so in a rectangular prism, won't white light split?
Ideally, we say no. But logic should tell us that the white light should split. And they should get somehow merged over here. I totally get your question, but I don't have a solid answer for this. I have to look up some researches for this one. But Ghazi, I know what you're asking about, but I don't have an answer for this.
Oh, okay, sir.
But it's a very interesting question. I appreciate that you came up with this. Every once in a while, not in all the academic years, I come across this question and I struggle. But at this time, I might actually look around this because I have a lot of free time to kill. Yes, Sadman. Yusuf bolo.
স্যার তাহলে ওই কোশ্চেনে স্যার ওই বলটা পয়েন্ট পি আসার আগেই ডিটেক্ট করতে পারবে লাইটটা।
What do you mean by point P?
In the question there was a point P and after he reached that point P he could see the light.
Yes.
Oh.
Yeah, bolo. Yes, he was moving from here towards P. He was not moving from here to here. He was moving from here in this direction.
Yes, sir.
Yes. And then he could detect the light P over here at this point. So if this was replaced with a blue light, he would be able to see the blue light a bit earlier.
Okay, sir.
Because blue would bend more compared to red. Acha, Fardin, tumi ei question ta korsila. Fardin, could I answer your question with the discussion that we just have had? Did Fardin leave? Acha, হ্যাঁ, Fardin বুঝছে. Okay. Abdullah, তোমার একটা কোশ্চেন হাত উঠাইছিলা, but did you get your question answered?
ক্লাস শেষ হওয়ার পর জিজ্ঞাসা করবি।
আচ্ছা ঠিক আছে, okay. The class is over. Thank you everyone for the additional 40 minutes of attention. Thank you very much. I will